In the previous lecture, we have discussed in very detail the Langevin theory of paramagnetism. And you have seen, finally, Langevin theory provides us Curie law, according to which the magnetic susceptibility of paramagnetic substances are inversely proportional to the absolute temperature. Actually, this chi, which is magnetic susceptibility of paramagnetic substance, that varies in inverse manner with absolute temperature T. But it was found that there are so many paramagnetic materials which do not obey this Curie law. That is, the temperature dependence of susceptibility in case of many paramagnetic materials is not like this. So definitely there is some fault, there is some drawback of the Langevin theory. Okay. So keeping this fact into mind, Weiss has modified the Langevin theory. You know, Langevin theory is a classical theory. So on the same line, on the classical line, Weiss has modified Langevin theory. And in this lecture, we are going to see the modification of Langevin theory of paramagnetism by Weiss. So the Weiss theory is not an independent theory. This is just a modification of Langevin theory. Okay. So if your aim is to know what Weiss has done, how he has modified the Langevin theory, so first of all you have to see what we have learnt in Langevin theory. So in this lecture I have actually mentioned all the results which we have obtained for paramagnetic materials in Langevin theory. You have seen that according to Langevin theory, the magnetization M of a paramagnetic material is given like this. We have obtained this result in our previous lecture. This is given as Ms times L of A. You know, M is the magnetization of the material, okay, which means the magnetic moment per unit volume. And Ms, this is called saturation magnetization. This is actually the maximum magnetization a material can acquire whenever placed in an external magnetic field. So this is the maximum or the largest value of magnetization, and this is equal to mu times n, where you know mu is the magnetic moment of each atom or molecule of the substance, and n is the number of molecules or atoms in unit volume of the specimen. Okay, and this L of A, this is called Langevin function. Okay, and you have learned that this Langevin function L of A is given by this expression. This is cot hyperbolic A minus 1 over A. Okay, this was the general result for the magnetization. Then you have seen that actually this A, which is equal to mu h over Kb times T, okay, where Kb is Boltzmann constant. You can see that this A depends on the magnetizing field H and also on temperature T. And this Langevin function is a function of A. So you can say that Langevin function depends on H and T. Okay, and if Langevin function L depends on H and T, then definitely the magnetization will also depend on magnetizing field H and temperature T. So in our previous lecture on Langevin theory, we have seen two particular cases, okay, and obtained the value of this M in those two cases. And what are those results? Let us see. First of all, we have considered that temperature is low and the field is high. In this condition, you have obtained that Langevin function comes out to be equal to 1. And so if Langevin function at low temperature and high field is equal to 1, then M will be simply equal to Ms, that is M is equal to mu n. So at very low temperature and very high field, we conclude that all the atomic or molecular dipoles align themselves along the line of a magnetic field. Okay, so the magnetization becomes highest. Okay, but when we have considered that temperature is very high and field is weak, then you have seen in the previous lecture that this Langevin function L of A is equal to A over 3. Okay, and so in this case M is equal to Ms times A by 3, and when you will put the value of Ms, which is equal to mu n, and A, which is mu h over kBt, then you find that the magnetization is equal to n mu square h over 3 kBt. Okay, and so susceptibility, which is defined as ratio of M and H, that is chi equal to M over H, that is equal to this much. This is n mu square over 3 kb times T. Here if you put C equal to n mu square over 3 kb, then this equation can be written like this. This is chi equal to C over T, where C is this much, and this is called Curie's law. So Langevin theory actually predicts this Curie's law, or you can say that Langevin theory supports Curie's law, or Langevin theory is in accordance with Curie's law. So from Langevin theory we conclude that the magnetic susceptibility varies inversely with absolute temperature T. Okay, and so if you will plot a graph of chi in against of 1 over T, not in against of T, when you will plot a graph of chi in against of T, the curve will be hyperbolic. But if we will plot a graph of chi in against of 1 over T, then this is equation of a straight line, you can see, and this straight line we will obtain in accordance with Langevin theory. Okay, but as I have told you that it is found that there are so many paramagnetic materials, for example compressed and cooled gases, solid salts, crystals, and many more. They actually do not obey this Curie law strictly. That is, if in case of these materials experimentally found value chi is plotted in against of 1 over tau, we do not get a straight line. In fact, it is seen that the susceptibility of such materials vary with temperature T in a complex manner. Okay, so definitely this Langevin theory fails in explaining the variation of magnetic susceptibility of so many paramagnetic materials in against with temperature T. Okay, so Weiss solved this problem, that how we can explain that the magnetic susceptibility of so many paramagnetic materials is not related with temperature by this simple relation which is called Curie's law. Okay, so what modification Weiss has done, let us now see. Actually, you have seen in the previous lecture that we say that the atoms or molecules of a paramagnetic substance have permanent dipole moment. But in the derivation of Langevin theory, we have not taken under account the interaction between the magnetic moments of different molecules or atoms. Okay, if this is one atom, this is another atom, this is another atom, each atom have magnetic moments. So definitely there should be a magnetic interaction between the atoms of a paramagnetic material. But in developing the Langevin theory, this magnetic interaction between the different atoms and molecules of a paramagnetic substance has been neglected. This was actually the fault of Langevin theory. If you want to get a correct classical theory of paramagnetism, then you must take under account this internal magnetic interaction among the atoms and molecules. And Weiss has pointed out this fact. So Weiss modified the Langevin theory by introducing a concept of internal molecular field. Actually, due to this intermolecular interaction, a magnetic field is developed inside the material. So whenever you will place the material, let us say that this is our specimen which has been placed in an external magnetic field, let us say H. Then at a point inside the material, the net magnetic field will be not equal to H, but an internal magnetic field is also produced at this point P due to the intermolecular interaction, because the molecules have permanent dipole moment, so they interact one another magnetically. So apart from H at this point P, there will be an internal field. So the net field at a point inside the material will be the vector sum of the external field H and the internal molecular field developed at this point P. Okay. So if you say that the internal field at this point is represented by the symbol Hi, okay, then the net field at point P will be equal to H plus Hi. That will be the effective field at a point inside the specimen. According to Weiss, this internal field Hi is proportional to the magnetization M. So you can say that Hi is proportional to M. Okay. And so Hi is given as lambda times M. Actually here this lambda is called molecular field coefficient. Okay. And so the net or effective magnetic field at a point inside the specimen of a paramagnetic material should be equal to H plus Hi, where H is the external magnetizing field and Hi is the internal molecular field developed in the material, okay, due to the intermolecular interaction between the molecules or atoms. Okay. So H effective, this will be equal to H plus Hi, and Hi is equal to lambda times M, so this will be H plus lambda M. Okay. So if now you want to find the correct expression for the magnetization and susceptibility, definitely the result for magnetization and susceptibility which we have obtained in Langevin theory, in those results H must be replaced by this H effective. Okay. So let us see. We have obtained the Curie's law here, and this in this equation E, that magnetization in accordance with the original Langevin theory is n mu square H over 3 kb times T. Okay. So if you consider the intermolecular interaction under account in accordance with Weiss modification, then in the expression of M, definitely this H must be replaced by H effective. Okay. So this equation E now can be written in this manner. This M is given as mu square N times H effective divided by 3 kb times T. Okay. But H effective, this is H plus lambda m. Actually, this H is in the this m is in the direction of H, because the material is paramagnetic, which is magnetized in the direction of the magnetizing field, you know. So both of these vectors are actually in same direction. So if you will write the magnitude of this H effective, then that will be simply equal to H plus lambda m, okay, or H plus Hi. So m is given as n mu square H plus Hi divided by 3 kBt, okay. But this Hi is equal to lambda times m, you know. So this Hi has been replaced here by lambda times m, okay. Now let us make the cross multiplication. When you will multiply this m by this factor 3 kBt in denominator in RHS, this will be 3m kBt, and that is equal to n mu square h plus n mu square lambda m. Our aim is to find m, so let us bring this second term in LHS and take this 3m into kb as a common factor. So this will be 3m kb times t minus n mu square lambda divided by 3 kb, and that is equal to n mu square h. And therefore you can say that this m is equal to n mu square h over 3 kb times t minus n mu square lambda over 3 kb, okay. This is the expression for magnetization after considering the Weiss modification or Weiss internal molecular field. Now once you have calculated the value of m, you can easily now find the value of magnetic susceptibility. You know, magnetic susceptibility chi is given by m over h. So when this m defined in this equation 3 will be divided by h, this h will cancel out, and the expression for chi will be simply n mu square over 3 kb times t minus n mu square lambda over 3 kb. You can see I have written it here that chi is equal to m over h, and this will be equal to this much, okay. Now this factor n times mu square lambda over 3 kb, this is written by the symbol theta c, and this mu square n over 3 kb, you have seen that this is Curie's constant c, okay. So replacing this mu square n over 3 kb by c and n mu square lambda divided by 3 kb by theta c, this expression for chi can be written like this. You can see, according to original Langevin theory, chi was obtained as c over t, but after Weiss modification, you can see chi is not equal to c by t, but it is equal to c over t minus theta c. Actually this equation is known as Curie-Weiss law, okay. This is called Curie-Weiss law. And here this theta c, which has a dimension of temperature, this is known as Curie's temperature, okay. This theta c is called Curie's temperature, or it is also known as paramagnetic Curie point, paramagnetic Curie point. Now see, this result actually gives so many interesting facts. If you consider that temperature T is less than this paramagnetic Curie point or this Curie temperature theta c, then what will happen? If T is less than theta c, then T minus theta c will be less than 0. That is, it is negative. And if it is negative, chi will be negative. But you know, the susceptibility of diamagnetic material is negative. So it is a very interesting result that a paramagnetic material behaves as a diamagnetic material when its temperature is less than Curie temperature. or less than paramagnetic Curie point. So this is a very interesting result which we find from this Weiss theory, that chi becomes negative at a temperature less than Curie temperature, and therefore we can say that paramagnetics behave as dimagnetics at a temperature below the Curie temperature. Okay, this is a very interesting result. Okay, but what is the practical fact? What we see in practice? Actually, in practice, it is found that most of the paramagnetic substances, the Curie temperature theta C is quite low. It is so low that this situation, that T is less than theta C, normally does not come into practice. So in practice, it is found that this T less than theta C is rarely found. It is very rare. Okay. So as T is generally not less than theta C, so a paramagnetic material does not behave like a diamagnetic material in general. Okay. So this is how this Weiss modification gives some new light, some new idea on the theory of paramagnetism. I hope you have definitely learned. Okay, so this is Weiss modification or Weiss theory of paramagnetism, which is also a classical theory. Now, after this lecture, we will learn about the theory of paramagnetism, but that will be actually the quantum theory. And you will see that quantum theory will actually give the very important facts on the actual behavior of a paramagnet. Okay, thank you very much.